R5, R4 is over. I showed R4 is a transitive relation on capital A. Here I am taking, or we are considering, look at the board, considering the set of I am taking this subset of A cross A comma B, A comma B, B comma A. Let us consider and the subset of A cross A, let it be R5. Now first element A comma B, this is the first element, this is the second element. First element is end with B. So starting with B, how many elements are there? First we start. Starting with B, only one element is there. That is what B comma A. Okay, according to procedure, just you strike out B comma B to say that striking out means here to say that both are same. That's all. It is one representation of the same numbers. That's all. Next, first element is A and A. So these two elements belongs to R5. Okay, is this first element A, last element A comma A again belong to R5. It is my question. Your answer is no. No means what? A comma A. If means what? Complete meaning. If A comma B comma A, that is belongs to R5, then this A comma A not belongs to R5. Hence R5 is not transitive. Is not transitive on capital A or A cross A. This is the best example for failure case of transitive relation on A cross A. Okay, once again I wish to recall the definition of transitive relation on capital A. What I said, if ordered pair of A comma B and B comma C belongs to R, capital R, then A comma C also belongs to capital R, then only capital R is transitive. Capital R is transitive on capital A. Where A comma B comma C, that is belongs to capital A. So this is the definition of transitive relation. This is the definition of transitive relation on capital A. Okay. One remark is there. It is a different point about transitive. What is that? If means perhaps this B comma C does not exist. I'm not telling about belong or not belong. I'm telling about existency. Does not exist. Does not exist. Then also capital R is transitive. Capital R is transitive. This is very important point. Okay, I will show one example for this statement. First, okay, capital R. First, capital A is the set of human relations. The set of human relations. R is defined as capital R is equal to the set of x comma y, so that x is wife of Y. So capital R is a subset of capital A. Capital A is what? It is the main set. It is about human relations. Here I took the relation wife. I took the relation wife. Capital R is, so first coordinate is lady. Second coordinate is gent. X is wife of Y. X is what? Female. X is what? Female. Y is what? Male. I am taking like that. Okay. Here transitive means let X comma Y and Y comma Z belongs to capital R. We have to define like that. After that we have to show that X comma Z is also belongs to capital R, and thus capital R is transitive. Capital R is transitive. So we have to show that like that. XZ also belongs to capital R, and thus R should be the transitive. Okay. 1 minute. So let X comma Y belongs to capital R. What does it mean? X is wife of Y according to given condition or given set. X is wife of Y. X is wife of Y means X is, who is that? It is a female. Next, Y is what? Husband. Husband means what? It is male. Y is male. Okay. And we have to take another element. YZ belongs to capital R. Letter YZ that belongs to capital R means what? According to given condition, Y is wife of Z. Y is wife of Z. Okay. According to this, who is that Y? Who is Y? Y is female. According to this condition, who is Z? Z is male. Consider, look at the board. Already we said Y is male. Is it possible to say that? Y already male? Y is already male. One male is wife of another male. Is it possible in this inverse? In human beings or in human relations? No, it is not possible. Therefore Y comma Z does not exist, or Y comma Z does not exist. I am not talking about belongs to or not belongs to. You look at the board. You come here. Once again, X comma Y belongs to capital R. Means X is the wife of Y. So in such a case, X is female, Y is male. You commit with Y is male. Next, in another element, you look at the board here. Y comma Z belongs to capital R. According to definition, Y is wife of Z. Means what? We are saying that according to definition or given condition, female is the wife of male. But here already we defined Y is male. Therefore Y is male. So male is wife of another male. Is it possible? No, it is not possible in the inverse or human relations. Okay, therefore bluntly we can say that Y comma Z does not exist. So even though perhaps Y comma Z does not belongs to or does not exist in capital R such relation, therefore capital R is transitive. transitive, capital R is transitive, capital R is transitive. So therefore, ultimately, if B comma C does not exist in capital R, even though capital R is transitive, it is the meaning of that sentence. This is the remark. It is one great thing in the definition of transitive. So, let us consider another example for this remark. You come here, just you take a singleton set, for example, R6, its name is R6. So the set of A comma B, that's all, single set. Okay, A comma B, that belongs to R6 and starting with B comma something, but this kind of element is not in R6. This kind of element is not in R6. So B comma something does not exist in capital R6, even though R6 is transitive relation on capital A. This is another example from our subset list. This one is out of example. Okay. Next definition, anti-symmetric relation. Anti-symmetric relation. So it is a small definition. Actually 2 divides 4. 2 divides 4 means 4 is 4 is divisible by 2. It is the meaning. Okay. I am asking a simple question. Is 4 divides 2? That is what? 2 is divisible by 4. Question mark. What will be your answer? No. Means what? It is not possible. When 2 divides 4 or 4 is divisible by 2. Okay. Next, let us take 2. 2 divides 2. 2 divides 2 means what? Once again, that is 2 is divisible by 2. Now, let it be small a, suppose small b. Take in reverse order. B divides B divides A. That is 2 is divisible by 2. Is it correct? Yes. Is it correct? Yes. Yes, it is correct. Why? Here. A is equal to B. A is equal to B. If A not equal to B, it is not possible. So, what I am telling that, if for example, we are taking the relation is divides especially on natural numbers. Relation is divides. If A divides, I am telling like that, if A divides B and B divides A, then A is equal to B. I am telling like that. It is my intention. My intention is, if A divides B and in reverse order, if B divides A, both are possible when A equal to B. If A not equal to B, then it is not possible to say like that. So this is called anti-symmetric relation. So what I am telling that if A comma B, that is belongs to, for example, I will write with a complete meaning. Let capital R is equal to the set of A comma B, so that A divides B comma A comma B, that is belongs to capital N. I am telling that if A comma B and B comma A, that is belongs to capital R, then A is equal to B. This is called, then R is called anti-symmetric relation on natural number capital N. Of course, it is not possible define like that on integer set, because in integer set 0 is there. That's why R is not anti-symmetric relation on Z. This is small definition about anti-symmetric relation. I wish to recall once again the first definition, reflexive definition. Reflexive definition means what? Let small a, that is belongs to capital A, if A comma A, that is belongs to capital R, then capital R is called as reflexive relation. So for example you come here, A comma A, we can write it as the set of A comma A, next B comma B, next A comma B. It is one of the subset of A cross A out of 16 subsets. Okay, it is reflexive. Once again, it is the reflexive. Say capital R, just like that. It is the reflexive. Now I shall prove that once again. This relation is a reflexive relation on capital A. So 1 minute, A is belongs to capital A, and A comma A, that belongs to capital R. Okay, finish. Next, B, another element is there. There, you look at the board. There, this is the basic. So our basic set, capital A is set of A comma B. So B belongs to capital A, and B comma B, it is also belongs to capital R. Okay, any more elements are there in capital A? No, it is stopped. Only 2 elements are there. I discussed the 2 elements A comma B. So out of 2 elements, first A belongs to capital A. Thus A comma A is also belongs to capital R. B belongs to capital A. Over. Only 2 elements are there. If another element C is there, then we can discuss whether C comma C belongs to capital R or not. It is out of question. At present, only 2 elements are there. So B comma B belongs to capital R. So according to these conditions, we can say that R is reflexive on capital A. Okay, finish. This is the definition of reflexive with beautiful example according to the basic. Okay, you can ask me, sir, what about A comma B? So we have nothing to do with the other elements in capital A. Just how many elements are there in main set capital A? Only 2 elements are there. For example, once again, A belongs to capital A. So is A comma A belongs to capital R? Next, B belongs to capital A. Is B comma B belongs to capital R? That's all. Okay, so we have nothing to do with this extra element A comma B in the definition of reflexive. Okay, next I will introduce another definition, identity relation on capital A. Identity relation. 1 minute. I will take yes S equal to R. We can write any letter. You can take R1, R2, R3, just like S, T. You can name it as your wish. You can take any letter. So S is equal to the set of A comma A comma B comma B comma B. Where is that A comma A B comma B? You start see here out of 16 subsets. It is there. A comma A, B comma B. I am taking this is subset. Look at the board. This is subset. Okay. Next A comma A. First coordinate is same as second coordinate. First coordinate is same as second coordinate. So for A belongs to capital A comma A is belongs to capital S. Next for B belongs to capital A, B comma B, that is also belongs to capital S. Enough. No, the set capital S should not have more than this number of elements. This is the vital difference between identity relation and reflexive relation. Once again look at the board. Capital R having the extra element A comma B, but capital S doesn't have the extra element. It is about this. It is the discussion about A comma B that belongs to capital A only. So once again, two elements are there in capital A. Small a belongs to capital A. Therefore, A comma A belongs to S. Next, small b belongs to capital A. Therefore, B comma B belongs to capital L. That's all. No more elements. Okay. Therefore, in such a case, S is called identity relation on capital A. Once again, let us take another example. For example, T is equal to only singleton set A comma A. Only singleton set A comma A. Observe this on capital A. On capital A. Why? Because already we are taking this. This is the subset of A cross A. Okay. Actually, A comma B belongs to capital A. I will put only two questions, namely number 1. For A comma A belongs to capital A, is A comma A belongs to T? Yes. Your answer must be yes. Okay. Next, second question. B, for B belongs to capital A, is B comma B that is belongs to T? No. It is no. Therefore, T is not identity relation on capital A. That is the difference. So, in different examples, you can search, you can understand the right definition of reflection relation and identity relation. Simultaneously, you can differentiate the definition, or you can represent the vital difference or minor difference between reflexive relation and identity relation. Okay, I wish to take another example. Capital X is equal to the set of capital X equal to the set of I will take again this A comma A, B comma B, comma A comma B. Let us discuss the set capital S. Okay. Basic A comma B, that is belongs to capital A. Right. For this, for A belongs to capital A, for small a belongs to capital A is A comma A that is belongs to S. Yes. Next, for B belongs to capital A is B comma B belongs to capital S. Yes. But A comma B, for A belongs to capital A will have more than one image, in capital X. Means what? image of A is A. Image of A is B. So A, same letter A will have two images in this set. Therefore, capital S is not identity relation on capital A. So by all means, let us consider identity relation. By all means, every identity relation is reflexive, but every reflexive relation is not identity relation. This is very, very important point. Next, equivalence relation. It is a very important definition. Equivalence relation means if capital R is number one, first one reflexive, and second one symmetric, and I am not telling R, and number three transitive, relation, then R is said to be an equivalence relation on the main set capital A. So therefore, reflexive is over, symmetric is over, transitive is over. If the given relation capital R is reflexive relation and symmetric relation and transitive relation, if these three conditions are satisfied, then only capital R is equivalence relation. Otherwise means if any one condition, if at least one condition is failure, then R is not equivalence relation. Mind it. For example, two equations are satisfied, third one is failure, or second one is failure, or first one is failure, then also R is not equivalence relation. This is the small definition about equivalence relation. And next, number one. Actually, you come here. Null set. First, our subset is null set. I am telling that null set phi is always equivalence relation. Next, number two. Actually, it is called void or null or empty relation. Actually, null set is subset of every set. Okay, it is in the set. Next, what I am telling that phi, it is called here in relations topic phi, it is called void relation or null relation or empty relation. Next, you come here. Last set, it is what? AA, AB, BA, BB. Sir, actually this is a total given set A cross A. Okay, of course it is A cross A. But what I said, every set is a subset of itself. So I am telling that in the second point, A cross A, it is also relation. Every set is subset of itself. Thus, A cross A, it is also one relation. This relation is called universal relation. Universal relation, because it is a complete set. It is total complete set of on capital A is equal to the set of A comma B. Thus, here A cross A means universal set is always equivalence relation. So therefore void relation and universal relation are always equivalence relation. Another one small definition, you look at the board. If capital R is equal to the set of A comma B such that A is here, A is from capital A and B is from capital B. Let it be like that. Is one relation on A cross B. Then its inverse defined as and denoted by R inverse, that is equal, just interchange first coordinate or second coordinate and R second coordinate as a first coordinate. So ordered pair of B comma A, so that A belongs to capital A, small b belongs to capital B. It is called inverse relation of capital R. Once again, let capital A comma capital B be non-empty sets and capital R is one relation defined on A cross B like that. Capital R is equal to the set of ordered pair of A comma B, so that A belongs to capital A and B belongs to capital B. Then its inverse is denoted by R inverse, just like that, and defined as the set of B comma A. Means what? Just reverse, we have to write in reverse order. B comma A, whereas A belongs to capital A and B belongs to capital B. This is called inverse relation of capital R.